In this video, we are going to briefly go over how Bayes' theorem can be used in medical testing and diagnosis. Please note that Bayes analysis is a much bigger topic than we really have the time to do it justice here. There is also a lot of arguments that you can find online discussing the validity of Bayesian and frequentist analysis. That is all well beyond the scope of this class. We're going to just stick to a much more black and white simplified version of this. I know we talked about these in the handouts, so please see that for more details. But as a quick overview and a quick reminder, sensitivity is the true positive rate. Or in other words, if someone has the disease, how likely is the test to read positive? This is distinct from specificity, which is the true negative rate. Or in other words, if a person does not have the disease, how likely will they be to test negative? Or in other words, how likely is the test to correctly state that they do not have the disease? So this leads us to our box of possibilities. The test can be correct, giving us either a true positive or a true negative, or it can be incorrect. And there are two ways that it can be incorrect. It could lead to a false positive, otherwise known as a type 1 error, or a false negative, otherwise known as a type 2 error. Oftentimes, if you make a test more specific, it can lead to less sensitivity, and vice versa. Though, of course, jumps in technology can lead to tests which are both more specific and more sensitive. When people talk about accurate testing, it's frequently used wrong. A test in and of itself isn't accurate. It has sensitivity and specificity. Its accuracy is related to the population that you are testing in, as well as the sensitivity and specificity of the test itself. This is where Bayes analysis comes in. If you did not watch the second video in your handout, please go do so now. The link is also in the notes of this slide if you need it. This is meant to be a quick summary of that video, not an all-inclusive coverage. The idea with this video is to say how concerned you should be if you go in for a test and get a positive result. Should your immediate thought be, I have this, or should it be that this is likely a false positive and not to be too concerned until further testing is done? When using Bayes analysis, you need to account for two things: the prevalence of the disease and how good your test is. As mentioned in the last slide, without accounting for how common the disease is, you cannot know the accuracy of the test. And its accuracy will vary based on the prevalence in the population. False positives are a much bigger problem when the disease is rare. False negatives are a much bigger problem when the disease is very common. The rarer the disease, the less likely it is that your test means you actually have the disease. A higher false positive rate will also make it less likely that a positive test means that you actually have the disease. So both have to be factored in. When trying to calculate this then, you need to know the chance that you get a positive test and have the disease divided by the total chance of a positive test. So to quickly walk through the calculation in the video now, the idea is that we want to know, given a positive test, what is the likelihood that we actually have this disease? So if we zoom out to what we are doing here, we're simply putting the chance that we got a positive result and have the disease over the chance that we got a positive result regardless of if we have the disease or not. Just like any other fraction, it's the thing that we care about over the whole. So here we are calculating the chance. If we are sick, we'll have a positive test weighted by the probability of being sick. We know that this test that we've kind of made up has a 100% true positive rate. So that'll just be 1. We know the rate of the disease is 1 out of 1,000, and so we can fill in the 1 out of 1,000. Then we need to calculate the chance that you got a positive result total. Or in other words, the sum of the chances of getting a positive result if you have the disease and the positive result if you don't have the disease. We already have our result of the positive test if you are sick, so we can just fill that in. Now, we just need to also find the chance of having a positive test given that you're healthy. To do this, we're going to multiply your 10% false positive rate, which admittedly is pretty high, by the proportion of the population that does not have the disease, or 0.999. Then, we'll add the two calculated terms up. So this gives us 0.1009. So now we have our probability of being sick and having a positive test from our last slide. And we have our chance of a positive test regardless if we are sick or not. So we can put the former over the latter. And this gives us a 1 in 100 chance of being sick, even after getting a positive test. If you want a few more examples of this sort of medical testing application, I've put a few in the slides. I made these up for past years as extra examples. It's looking at different tests for different fetal trisomy conditions. It may be interesting to you if you or someone you know are planning to have a baby anytime soon. The short answer is, much like the last example, a positive result generally still means that your baby is totally okay. And that getting a positive result causes a lot of parents a lot of stress and anxiety, when really they should just relax and not be concerned until later better tests can be run to determine if there are other markers for the condition. It's particularly important for parents to understand this, not only due to stress, but because in so many cases when a trisomy is discovered, the parents opt for abortion. If they don't fully understand the odds, they may opt for an early abortion when perhaps it would have been better to wait for the better tests that can be done later in pregnancy. I think regardless of your pro-choice or pro-life stance, no one wants parents to abort a baby based on a false positive test. When these screening tools test positive, parents are always offered better diagnostic tests of CVS or amniocentesis. These, however, do come with risks, and so they need to be avoided whenever possible. If you'd like to see the math on this, I'll refer you to the course slide links. Feel free to ask more questions about this in class if you'd like, but I'd like to use a different example for this year as the focus for our video. Take a moment and read through the results and conclusions of 2 studies. I've posted the links here and in the slides if you want to read the article's full text. I don't know that it is particularly necessary for our purposes here for you to read the entire articles. If you'd rather pause and read straight from the video, I'm going to go ahead and leave this up for 5 seconds, and then I'm going to switch to the next slide for 5 seconds so that you can pause on that slide and read this as well. As you're reading through, think about what I talked with Bayes analysis. The tests have varying false positive rates. The best case is likely around 1%, and that was what was reported for the tests used in the Santa Clara County study. Write your thoughts on the activity sheet to discuss with your groups. Personally, I'd pull up the slides from the Google Drive folder and read and have the text handy. After you've read through, come back and I'll give you some more specific questions to think about if you're feeling a bit lost as to what I'm trying to point out. And eventually a reading that points it out directly and gives you a very cool tool for doing this sort of thing. So pause now and come back when you're ready for some hints. I'll move to the next study in 5 seconds to give you time to pause easily there too if you're reading directly from the slides. If you saw what I was getting at with these 2 articles, awesome. If not, let's chat a bit more about them. These were done with pretty similar tests, with pretty similar specificity and sensitivity. For the sake of argument here, let's just go ahead and say that each test had a 1% false positive rate. In which population is this false positive rate going to cause larger relative errors? And if you're up for running the math on your own, is there either of these studies that you simply wouldn't trust the numbers on at all? Take a moment, try to answer this for yourself, think about it for yourself, and then we'll move on. And I'll give you an article to read and some more hints. The first paper was a really, really big deal when it came out. Using their numbers meant that so many more people had been infected than what was previously thought. This had massive implications for the death rate and rates at which we were reaching herd immunity. After all, if more people had been infected but had not been gravely ill or died, then that meant that the virus was not nearly as deadly as the hospital numbers were showing. Similarly, if many, many more people than we'd previously thought had been infected, we were much closer to reaching herd immunity. Both of these are incredibly important findings that made news instantly, especially as it actually confirmed many people's thoughts. I had actually personally guessed that this was more widespread than we knew at the time, but this paper was mind-blowing even compared to what I had guessed. Except that it wasn't. Because even though the tests weren't particularly bad, the prevalence was very, very low in Santa Clara. Higher than most places in the nation, but low enough to cause issues with the testing. So this meant that the false positives created huge errors in the research numbers, and without incredibly careful statistics and reporting of uncertainty, it effectively created a false narrative about the virus prevalence in the county. There is also some arguments about how good the tests really were, which is why I've generally been using phrases like, for the sake of argument, we'll assume a 1% false positive rate. In reality, that's not necessarily decided on. Now, if we contrast the situation in Santa Clara to the New York area, we're now in an entirely different population. If we think back to our Bayes analysis formula, we are completely changing that term that weights the probability of being sick. And this dramatically increases the likelihood that if you test positive, you also have the virus, simply because it's far more likely that you have the virus. So this paper wasn't perfect, and it likely overestimated prevalence a bit due to limitations such as recruiting people who are in the environment rather than quarantining completely. But it was likely much closer to the true numbers than the Santa Clara study. This article effectively says what I just said on the last slide. Take a moment and read it if you'd like. As always, link is in the slides if you need it. If you are content with my explanation, you can feel free to skip the article, but do go and visit it. And here's why. I want you to go and scroll down all the way to the bottom, where they have this really cool little tool to help us think this through. I've also added 2 links to the slide notes, which include a bit more detailed discussion of the issue in general, and then a really, really deep dive into the nitty-gritty analysis of the statistics, and the updated paper that they fix some issues. These aren't particularly necessary to read if you don't want to, but I just felt like for completeness sake that they should be included for people who wanted some assistance digging in a bit deeper into these concepts. Now, sticking with the NPR link listed here, and using the slide calculator tool. Here's what I would like you to do. Assuming that the test had a false positive rate of 1%, how accurate was the test in Santa Clara County, and how accurate in New York? Of course, we don't have an exact prevalence data, but you can use the numbers from the study as a good estimation point. You may also want to report it as a range. There isn't one exact answer we're looking for, just a general estimation. Then I'd like you to take this concept and instead of applying it geographically, apply it to risk groups. So for instance, say you have people who completely socially distance. They go to the grocery store max once every 2 weeks, perfectly mask wear, and keep more than 6 feet whenever they're around other people. And their entire households do the same. Think about the prevalence of COVID in that group of people and how that changes the accuracy of antibody tests. Now consider your high-risk groups, people who are in healthcare fields, other essential workers who are not given appropriate PPE, restaurant goers, church goers, bar goers, gym goers. How is the accuracy of the test going to compare in this group to the low-risk groups? You can relate this to our discussion of the 2 groups of people that we talked about in Santa Clara and the Northeast metropolis. Now, taking into consideration everything that we've talked about so far, what problems do you see if people in low prevalence areas take positive antibody tests as a go-ahead to resume normal life without appropriate mask wearing, social distancing, and other preventative measures, especially for those who have underlying conditions? If you need help working through any of these discussion questions, stop by class. I'm going to avoid discussing it here in order to not stifle any group discussion on the matter. This has been a pretty dense video, so let's do some key take-home point summaries. The accuracy of a test is dependent not just on how good the test is, but also on the prevalence of the disease in the population. A test which is 99% specific and sensitive may sound really good, but if it's done on a population with extremely low rates of the disease, it may still produce mostly false positives. This means when you get a positive test result back for a very rare disease, you want to consider that more likely than not, you still don't have the disease. It also means when doing studies with prevalence studies on rare diseases, these false positives need to be factored into the analysis. I don't want you to think that you can't still get good data from these tests. You can. You just have to account for it while doing the analysis. For the most part, this means that a test isn't going to be able to tell you accuracy. The tests can instead state specificity and sensitivity, and then doctors, researchers, and patients need to use prevalence along with what is called pretest probability to analyze how much a trust should be given to a specific test. The understanding of how Bayes analysis is affected by pretest probability is an incredibly important part of medicine. If the pretest probability is high enough, a negative test may be ignored completely. For example, if a patient has been exposed to someone with a highly contagious disease and is now showing all of the symptoms, even after receiving a negative test result, doctors may deem it appropriate to assume a false negative. And with that, we're going to end our discussion of Bayes analysis. This tends to be a topic that people have a little bit of trouble with, so please, please, please feel free to submit your answers wherever you can. If you're most comfortable asking it on the slides, that's great. If you're most comfortable asking it on the Google Doc for the handout, That's good. Google form, perfect. Or just come to class and ask it to us in person.